An interesting application of magnetic fields and forces is the Hall effect. Why is it an interesting application? Well, it's how a lot of our magnetic field sensors work. We use magnetic field sensors in the lab that work because of Hall effect. It's used in some medical techniques for measuring blood flow. And it gives us one more piece of evidence that it's negative charge carriers that move in our typical metal conductors and not the positive charges. So let's take a closer look at the Hall effect. If we have a region of magnetic field and we put a conductor through it and run a current, the current feels a force in that magnetic field. And those charge carriers move in the direction of the force. So we'll get a charge buildup at the top of this conductive ribbon and at the bottom of this conductive ribbon. And we can measure the potential difference with the voltmeter. And if we know something about the geometry and the width, T, of this conductive ribbon and the current, we can determine the magnetic field strength. First, let's take a look at the case where positive charges move in our metal conductors. Current to the right, I've already said that in this situation I have current flowing to the right through this metal ribbon conductor. Current to the right, if positive charges move in our circuits, well, they're moving to the right. Current is the direction of positive charge flow if positive charge is moved. So current to the right means positive charges are moving to the right. A positive charge moving to the right will feel a force toward the top of the page. So positive charges feel a force up, they will move up, and I will end up with positive charges along the top of this conductive ribbon. They feel a force in that direction. The whole conductive ribbon feels a force in that direction. And if the positive charges are moving up, then we're going to be left with some negative charges back here behind on the lower side of this conductive ribbon. Get out our voltmeter, measure the potential difference, and we'll see that the top of this conductive ribbon would be at a higher potential than the bottom if positive charges were moving to the right. Now let's take a look at the situation where negative charge carriers are actually moving in our circuit. A current to the right, remember we're still using current to the right in both cases. A current to the right means if negative charges are actually moving, negative charges are moving in the other direction to the left. So a negative charge moving to the left feels a force in this magnetic field. What direction is the force? Toward the top of the page. So either way, this metal conductor, whether it's positive charges moving to the right or negative charges moving to the left, either way, this metal conductor feels a force toward the top of the page in this magnetic field. If the negative charges are moving and feel a force pushing them toward the top of the page, they will end up along the top of this conductive ribbon, leaving positives behind on the bottom. If we hook up our voltmeter here, we'll get the bottom of the ribbon is at a higher potential than the top. And of course, this is what we see when we do the experiment. Negative charges are actually moving in our typical metal wires and conductors. You're probably wondering, how do we use this to measure the magnetic field? Well, it turns out that the potential difference across our conductive ribbon, the potential difference across the thickness of that conductor, is equal to a coefficient called the Hall coefficient multiplied by the current, multiplied by the magnetic field, and divided by the thickness of that conductor. So if you properly tune your apparatus, you can measure the magnetic field strength of an unknown magnetic field.